All right, this is part 2 post fire drill. We had this one here and we got it down to there. So this would be the area that has all the decreasing functions. If you were to actually graph that, you'd go to 2, you'd go down 2 over 1, you'd draw this line in, and less than would be under that. So you can start to see where all the negative slopes were under that line, and above that line were all the positive slopes. So this actually kind of goes back to an old algebra technique you would have used where you graphed and shaded, and that actually works out. So now C says find the second derivative of the function. So take the first derivative and we're going to take the derivative of that. So our second derivative here will be the derivative of 2x, which is 2, plus derivative of y, which is dy dx, and then the derivative of negative 2 is 0. Now we don't want to stop there. We want to go 2 plus and actually put the derivative back into here. We want to put 2x plus y minus 2 in where the dy dx was. Okay, so again, where did I get that? It was just what was given to us from the beginning. I just sub that back in. The 2 and the minus 2 cancel out, so our second derivative actually is just 2x plus y. So right inequality represents where the function is concave up. We're going to be concave up when our second derivative is positive. So when 2x plus y is positive, or in other words, when y is greater than negative 2x. So negative 2x would be the line right here. It goes down 2 over 1. All right, and when y is greater than, so in fact everything you see should be concave up, and that's kind of what we see. We see these concave up parts here. If we were to graph the slope field in this area, we would start to see some concave downness. But that's how we handle that. This one gives us a different differential equation. They say find the slope field for this. So if we were at the point 0, 0, we'd have no clear idea. So they're not going to ask you to do 0, 0 because we wouldn't have an idea of that. But when x is 0, when you're on the x-axis, when you're on the y-axis, when x is 0, our slope is 0. So both of those should have been flat line 0 there. When y is 0, which is on the x-axis, then we should have undefined slope. We should have vertical slopes there. So this is what you should have for that. Okay. Now, when x equals 1 and y equals 1, we get a slope of 1. When x equals 2, y equals 1, we get a slope of 2. Then we get a slope of 3 here. When x is 1 and y is negative 1, we still get those same slopes because of the squaring of y. When x is negative 1 and y is 1, we get negative 1, negative 2, negative 3, and then the same thing here. So that's what our slope field should look like. All right, find the second derivative. We're going to do quotient rule on that. So quotient rule says our second derivative would be bottom times derivative of the top minus top times derivative of the bottom, which is 2y times dy dx over bottom squared. So that should be the start of our second derivative, and then we want to replace that dy dx with the original derivative. So we're going to get y squared minus 2xy times x over y squared all over y to the fourth. You're welcome to leave that, or if you want to cancel this with one of those and make this 2x squared over y, that's fine. What some people will do is they'll multiply top and bottom by y to get rid of that denominator there. So they'll end up with something like y cubed minus 2x squared over y to the fifth. Again, that's multiplying top and bottom by y, but you don't have to do that. This is perfectly fine here, as is that. All right, then we were given this slope field and we were asked to trace the solution through these 4 points here. So when we trace a solution, what we're doing is we're just following these slope lines. We're just letting the equation kind of flow with them. And once the lines start to turn like this, then we turn our equation as well. What you don't want to do is you don't want to just power through a line, crossing through it. That's not the idea. We want to let the line kind of direct us and bend us to wherever we are. So maybe I could have even had it come down a little bit more like that, but then we turn it. All right, and you can see that it kind of follows this channel here up kind of like that. Okay, doesn't have to be picture perfect, but it does have to kind of follow close to that. We can't, like I said, have this come down and break into here. From this part Same thing, we're following this slope line here, and then it brings us into this channel, and then it goes up just like that other one did. Okay. For this one here, we're coming down the slope line for a while, and then it starts to bend, and then we get into here, and once we get into here, it starts to break down and go like that. So there's our solution for that. And then for this one, this comes up and starts to turn, and then it gets in there and follows that channel there. So that's what those solutions should have looked like. And then our last one wants us to confirm that this is indeed a solution to that. So we need the second and the first derivative for this. So if I go first derivative, it's going to be the derivative of natural log of x to c. That derivative of natural log is 1 over x to the c times the derivative of that, which will be c x to the c minus 1. Now that's a little strange because we don't have a actual number to work off of. So I'm going to try to help you here. We have a c, x to the c minus 1 over. Now if you were to think, like, let's say c was 5, then this would be x to the 5th and then x to the 4th on top. If this was c was 10, this would be x to the 10th and x to the 9th on top. No matter what c equals, you have one less x on top than you have on the bottom. So these x's will cancel all of these and leave us with just one x on the bottom. C is some constant, x is the variable we're working with. So this would be our first derivative. Okay. And I could rewrite that as cx to the negative 1 if I wanted to help me with the second derivative. The second derivative for this will be negative cx to the negative 2, which is negative c over x squared if I want to write it like that. Okay. Now let me bring this over. So we're going to have x times the second derivative, negative c over x squared, plus the first derivative, c over x equals 0. So this x can knock out one of those. I get negative c over x plus c over x equals 0, and that indeed works out. Makes it much easier if you do this simplifying here. If you don't do that simplifying, then this is a very difficult problem.